Okay, in this video we're going to do a few practice Lewis structure problems. So in my first example, I'll do the nitrate ion, and every single time I know I mentioned this before in other tutorials, but every time you're doing a Lewis structure, it's 3 steps: valence, get the skeleton, and then add dots to fill octets. And then last thing to do is you check your structure and see, count your structure and then see if are you over or under. Alright, so 6 times 3 is 18 plus 1. So this would be 24 valence electrons. Okay, so our structure needs to hit that number at the end. So put N here, connect the oxygens, and then start adding some dots. I'm on step 2. And now we count, and we see if it matches 24. I can tell we're gonna be over by 2. So there's 8 here, 8 here, and 8 here. That's 24 already. Plus we have 2 more here. So we have 26, and we need to get to 24. So what that means is we need to erase those and then add another right there, and it should work. And so next thing to do, the very last thing, it has to pass 2 checks. You got to assign formal charges and make sure that they sum up to the overall charge on the whole atom. This oxygen, I think I forgot to erase a dot there. So this oxygen is going to be 0. This nitrogen is going to be a +1. So it's 5 minus 1, 2, 3, 4. So it's going to be +1. This oxygen's a -1, and this oxygen is a -1. So overall, we have a -2 and a +1. So overall, it's a -1 charge. Okay, you'll notice that you can actually draw 2 equally to like 100% equivalent structures, 2 more actually. So the nitrate ion does something called resonance. So resonance is when 2 or more Lewis structures are 100% equivalent. So the nitrate ion could also do this. So you could put the single here, and you could put the double on this one, and it can also do this one where we have the double on the right or the right oxygen, the one on the right side. Okay, so it could do, actually these are all exactly equally likely. So they have the same formal charges, they all follow the octet rule. All that happened is this double bond like shifted. It could be just as likely be on any of those oxygens. So that's resonance. Okay, let's look at a couple more examples. Not everything will do this. These are just like special cases. You just kind of have to like draw the Lewis structure and then see if you can rotate that bond around. A lot of the non-metal oxygen compounds do it, like the carbonate ion does it, the sulfate ion does it, the phosphate ion does it. So a lot of those oxy anions do it. Okay, so let's look at another example. Br3, this is an actual polyatomic ion, so Br3 with a -1. So step 1 is always valence. So this is actually in column 7, so times 3. We have 21 plus 1 more, so we have 22 valence. Next thing is let's get our skeleton structure and then add dots to fill the octets, and then check to see if we're over or under, and adjust accordingly. So we'll put BR here, another one here, another one here. So we did that. Now we're going to add dots to fill the octets. I can already tell we're going to be under, so this is the first time this has happened so far. So we have 8 plus 8, that's 16, plus 18, plus 2 more, that's 20. So we're actually under this time. So when you're under, if you remember from the other tutorial, if you're under, you add lone pairs to the central atom. So you take your BR in the middle, and that's all you do. You just add another lone pair. So I'm going to erase that and put it like this, and you add another lone pair. So you'll actually notice that this is actually breaking the octet rule, and this is called hypervalent, which this is actually allowed for, so it's not uncommon for elements below row 3, and it's hypothesized, and this is backed up by some experimental data. This is kind of like new research actually, but this is it's hypothesized. Why is this so special, being below row 3? So what typically happens is you get crowding of electrons. If you try to go past an octet, there's just too many electrons around the atom. So, and all these electrons are negative, so you have negative, negative, all these negative electrons everywhere. Okay, so there's just too much repulsion, and it might be unstable. However, if you get below row 3, if you remember from our periodic trends, when you start going down a column, okay, so here's row 1, 2, and here's row 3. So when you start getting to these types of atoms, you start to get really huge atomic radii. So Br, for example, has, let's see what row bromine is on. Bromine is on the 4th row, so it's going to have 4 rings. So in that case, so 1, 2, 3, 4. So you see, when you have a big radius like that, you can actually, you could actually fit. It has another Br here. There's a Br here. So you could actually like fit some extra electrons in that radius. So these electrons, and then this is going to have a bond here and a bond here. So they're actually like really far apart, and it could be actually somewhat stable and allowed. So hypervalency. So hypervalency is it works when the radius is big, the central atom. Okay, because of less crowding. Of electrons. Okay, so let's try one more example. Let's try. Actually, I'll have you guys try this one, and then I'll have you guys also try this one. Oops, not that one. Don't worry about that one. That was a mistake. The slide switched on its own. Okay, and then so try this one, and let's go with this one. This is called the cyanate ion. Okay.